Hello, my name is Dimitrios Velenis, and in this presentation I'm going to discuss about the efforts we are taking in the HiCONNECTS project to establish a pilot line on the heterogeneous integration photonics. I will start this presentation by discussing why photonics are already playing a very important role on our everyday life and how this role is expected to become even more significant in the future. Today, we see a tremendous increase in the amount of data that is being exchanged. Even now, as you watch this webinar, there is data coming to your computer, so this contributes to the overall global data traffic. We generate data as we talk also with our colleagues on video conference, as we check the news or our emails on the way to work, as we exchange content with our friends and relatives on social media. Also, in these days, with the increase on the amount of AI and machine learning applications, there is tremendous increase on the amount of data that is used by those applications and also on the computational power. The heart for all this data traffic and AI queries are the data centers. The data centers are the physical facilities where data is stored, managed, computed, and also delivered from to the different applications and services. For the future, the data centers, they need to meet three primary requirements. The first one is to increase their data bandwidth in order to keep up with the requirements for a global data growth. Also, with the increase requests for AI and machine learning applications, they need to increase their computational needs, and they need to do all of that in an energy efficient manner in order not to consume the whole energy that is being produced by mankind. Within the HiCONNECTS, we're actually looking at all of those challenges, and in the pilot line 2 developments, we are actually targeting applications that will go into the data centers of the future, such as the next generation smart networking card and switch platform by NVIDIA. Next, I would like to discuss a little bit how electrical interconnects are addressing those challenges and why photonic interconnects can be a best solution for these requests. This is one way to describe the problem. Every compute processor that is built today has the architecture around the idea that data is being moved using electrical interconnects. However, there is a bottleneck that is created by the electrical interconnects. And the first one is shown on the top picture here, where we see that the power for off-chip interconnects for sending and receiving data outside of the chip is actually has reached the limit of the total power allowed per package because of the high bandwidth that is being required. The second point for the bottleneck is the fact that the performance of electrical interconnects is dropping with distance, and this has also an impact as we are targeting higher bandwidth rates. I would like to talk more about this second trend in the next slide. In this slide, we saw the previous trend, but now with some references from industrial data. The y-axis here is the figure of merit, which is the edge bandwidth density multiplied by the energy efficiency of the interconnects, and on the x-axis we see the interconnect distance. Data center is structured very hierarchical, requiring interconnects from the chip to the package, to the board and rack level, also to the level of the server cluster, and then to the entire data center. And we see here that although electrical interconnects have been pushed to a really high performance in the latest years, they reach their limit, which is indicated here with the orange line that defines the I/O wall. As we request more and more data bandwidth to be available to serve the increased data growth, especially on the distances here in the middle level, on the board and rack level, and also on the cluster, electrical interconnects here are not meeting up with the requirements in terms of data traffic. What can be an alternative solution here is the photonic interconnects, where however, we need to increase their performance in order to meet the requirements at this range. In HiCONNECTS, we believe that this can be achieved using co-packaged optics, where the photonic chips together with electronic chips and higher density optics can be brought together in order to increase the performance of the optical interconnects on this range, and also the energy efficiency, and also move the application of optical interconnects onto the low distances where much higher data rates are required. Here we see more of the landscape for the optical interconnects, and here is again a plot of the link bandwidth with respect to the link distance. We see that for the largest linked distances, those are dominated by the optical interconnects, and actually by switching from multi-mode fiber to the single mode fiber, we are achieving higher increase on the bandwidth. However, as we move to on the board and package level, there we see that if we want to keep on increasing the data bandwidth as required by the increase on the global data traffic, we probably need to switch from electrical interconnects shown here in green to the optical interconnects shown here in blue for the next generations. And here are where we need to do some also improvements in the optical interconnects to meet the challenge that we have. In the HiCONNECTS project, we were on to work on enabling the optical interconnects to meet this mission. For this reason, we're going to establish a pilot line for the heterogeneous integration of photonics targeting co-packaged optics that will bring us to the next generation of short-reach optical interconnects. Within the pilot line, we're going to be looking on the requirements regarding the introduction and integration of new materials and how those are compatible with the existing materials used for photonics. Also going to be looking on solutions regarding the heat generation and heat dissipation for photonic devices. And as we're going to be looking onto assembling of components onto each other to achieve the co-packaged optics, we're going to be looking on the accurate placement of those components. Finally, all the processes that will be developed, they need to be clean and compatible with the process flows that currently exist for photonic components. All of those activities are also going to be targeting a higher TRL level, looking to be demonstrated into the development of a new smart networking card and switch applications by NVIDIA that will go into the data centers of tomorrow. As the foundation for these developments, we're going to be using the Silicon Photonics technology platform that is offered by imec. This is a quite mature platform based on processing on 300mm wafers and has available a series of different photonic components, as you see on this slide, that include high-density silicon waveguides, wavelength division multiplexing filters, integrated silicon nitride waveguides, edge couplers and grating couplers for bringing the light in and out from a photonic IC. Also, active devices such as germanium based photodetector, and also a range of modulators offering different figures of merit in terms of bandwidth performance and energy consumption. We will be using the Silicon Photonics platform as the foundation for the pilot line on the heterogeneous integration of photonic components in the HiCONNECTS project, working together with all the partners that you see on this slide. The developments will fall under two main categories. One of them are the silicon-based photonic components, targeting mostly the co-packaged integration of photonic components serving higher bandwidth of optical interconnects, as shown here, together with the integration of the light source into a photonic IC. The second category will be based on indium phosphide photonic components. This is actually serving also the heterogeneous integration aspect of the pilot line that will further enhance the performance of photonic interconnects. And for those components, we're also going to be looking into the developments that will happen on the pilot line, one of the HiCONNECTS project targeting the RF electronics. Let's see now with a little bit more details the different activities we're going to be taking within the framework of the pilot line. We are going to be working on silicon photonic components for co-packaged optics, where we're going to be designing a photonic IC and co-integrating with an electronic IC for driving the photonic components. On this same build-up, we're looking to assemble a fiber array with a high count of fibers that will serve the high bandwidth application intended for these components. Also, we're looking to assemble and to integrate into the photonics platform the light source by using quantum dot DFB laser arrays. We're also going to be looking for the indium phosphide components to develop high-speed lasers and high-speed photodetectors targeting heterogeneous integration. And we're also going to be looking on a novel indium phosphide membrane platform to develop an in-phase quadratic PIC based on Mach-Zehnder modulators. Next, let's look on these activities into a little bit more detail. Let's start with the silicon photonic components for co-packaged optics. Here we are looking for the development of a transceiver based on silicon photonics with a greater than 50 GHz bandwidth. For this transceiver, we're going to be building a photonic IC with different photonic devices matched with an electronic IC that contains the driver and the transimpedance amplifiers that are required for functioning those components. Both of the chips will be designed by imec, and the photonics chip will also be built using the imec Silicon Photonics platform. In the processing of this photonic IC, we will be looking for inline metrology and characterization that will be provided from the HiCONNECTS partners that are listed here, such as NOVA, KLA, the Semilab, and the Polytechnic University of Bucharest. Also, on the co-packaged optics build-up, we're looking to assemble a high fiber count array. This is towards the development of a scalable fiber assembly solution using wafer-level processing. For this work, we are relying on the photonics plug and photonics bump technology developed by Terramount, and also on the assembly capabilities provided by FIX in order to have assemblies with accuracy tighter than 1 micrometer. Another activity is the integration of the light sources into the co-packaged optics. The light sources can be seen as the optical power supply for the silicon photonics chips. imec is going to be building a photonics chip that contains the interface for the laser arrays as shown here, and the laser arrays themselves will be coming by Inolum that they're going to develop gallium arsenide-based quantum dot DFB lasers. The lasers will be assembled on top of the silicon photonics chip using the high precision assembly technology by ASM Amicra and targeting tolerances below 300 nanometers. We're also going to be looking for inline metrology of the laser interface that will be provided by the KLA ICOS. As we mentioned already, we're also going to be looking at the developments of the pilot line 1 of the HiCONNECTS project to integrate indium phosphide optoelectronics with electronics. The first application will be the development of high-speed direct modulated lasers with greater than 100 GHz bandwidth. This will be based on the novel concept of flip chip compatible dual DFB laser with integrated passive optical feedback, targeting baud rates higher than 200 gigabaud. This activity will be a collaboration of the Fraunhofer that will be building the DML chip, the Ferdinand Braun Institute that will be looking into the high-speed electronics, Eichstrom will be providing support with the regrowth optimization, and DeepScam will be doing the analysis of the p-contact metal semiconductor interface. We're also going to be looking on indium phosphide components to develop high-speed photodetectors for heterogeneous integration. Here we're looking at direct detection of 8 WDM PAM4 modulated signals targeting 200 gigabaud rates. And here we're looking for a heterogeneous integration of an indium phosphide chip containing the transimpedance amplifier and the DMUX together with a indium phosphide photodetector chip that is shown here. The application will be targeting 200 gigabauds from the photodiode to the DMUX and 50 gigabauds at the PCB. This activity is a collaboration of the Fraunhofer that will be building the photodetector chip. The high-speed electronics will come from the Ferdinand Braun Institute. Ekstrom will be working on the antimony growth, and Thermo Fisher will be doing term analysis of the doping interfaces, while DeepScan is going to be doing analysis of the gold tin flip chip microbumps. The last but not least activity going to be taking the pilot line 2 of the HiCONNECTS project is the development of an in-phase quadratic transmitter based on Mach-Zehnder modulators for coherent communications. This will be done utilizing the indium phosphide membrane or IMOS platform, and the application will be targeting more than 50 gigahertz of bandwidth. This activity will be done in collaboration by the Eindhoven University of Technology that will be providing the laser modulator chip. The epitaxial growth processes will be done by Ekstrom, and Bruker will be doing the inspection of those processes. For the IMOS platform, the bonding process that will be required will be provided by EVG, and the strain measurements on this material will be done by the Polytechnic University of Bucharest. So at this point, I would like to bring to the end of this presentation. So in summary, on the HiCONNECTS, we're developing a photonics heterogeneous integration pilot line, what we call as the pilot line 2 of the project, targeting new developments on advanced co-packaged optics. We are in this process, we are relying on the state-of-the-art 300mm Silicon Photonics technology by imec, and we're using that platform to co-design and develop co-packaged photonic and electronic components, also to integrate on those components, on those co-packaged modules, the high-performance light source, and also scalable fiber assembly concepts. We are also looking to collaborate with the pilot line 1 from HiCONNECTS to enable indium phosphide heterogeneous integration, and all of those activities are targeting a higher TRL productization level with the smart networking card and switch components that are targeted by NVIDIA into this project. As a last word, I would like to thank the KTT joint undertaking for the support to all of these activities, and I would like to thank you for your attention. Thank you. Thanks a lot.